Welcome back. This is part 2 of section 8.3. For this, we're going to be talking about the center of mass. This first page is more or less an introduction to what center of mass is. And our goal is to find a point on a plate that represents the entire mass itself, called the center of mass. Sometimes it's called the centroid if we're in 3D. Now suppose that a rod, so this is just a one-dimensional rod, lies along the x-axis with the first mass at location x sub 1 and the second mass location at x sub 2, meaning they're potentially different distances and different masses than one another. And we want to find the center of mass is x bar, meaning we want to find where that balance point is, where if I have something heavier and it's closer, but I have something less heavy and it's further away, how can I make them balance out as we do that? The distances from each of the fulcrum is going to be x bar minus x sub 1 here. The other one is x sub 2 minus x bar. And you can see when I set the two equal to one another, when I take the mass times the distance away from the fulcrum, and I want to make them balanced, and I do a little bit of algebra, I end up here with my formula. Now, the numerator is what we call the moment. Meaning comparing the mass and how far away it is and adding those up. That overall is called the moment. We'll talk more about that in just a moment. The denominator is the overall total mass. And that will be true even when we don't just have 2 points, but when we have more than 2 points. And I talked about the moments of the masses relative to the distance away and the total mass m sub 1 plus m sub 2. So let's generalize a little bit. If we have a system of n particles with masses m sub 1 all the way to m sub n, located at the points x sub 1 all the way to x sub n on the x-axis, then what we have here is our balance point, our center of mass, is going to be adding up all of the moments and dividing by the overall mass. Now, this we're calling the moment of the system about the origin. And in one dimensions, it's not all that interesting. It's, in fact, even intuitive, I would say. 2 dimensions, it gets a little bit more complicated. So we're going to consider n particles, each with its own mass, and they're located now at an xy coordinate system. So now we have 2 systems going on here. We have an x direction and we have a y direction. And what we're going to end up with here is our moments. Now, this might look a little bit weird. We're going to define the moment about the x or the y-axis, and we're adding up the x pieces. Let me explain why that is. Here's the y-axis, and we want to know the mass, how far away the mass is from the y-axis. And you can see the distance from the y-axis is going to be x. So that's the reason why it's x is here with the m sub y, and the opposite here, m sub x, is going to be the distances from the x-axis, so you get the y's there. So I know it says x-axis, m sub x, and then we have y's in there. It looks backwards, it's actually correct. And the coordinates for the x and y for the system is each are divided by m, which is the total mass, meaning add m sub 1, m sub 2, m sub 3 up. And then we get the moments and divide it. So x bar, the x coordinate, is going to be the moment about the y-axis divided by the overall mass, and y bar, the y coordinate of the center of mass, is going to be the moment with respect to the x-axis divided by the mass. So there's the theory behind all of it. Let's jump into some examples how we're going to do this. Now, I want you to sort of picture, if you will, we have masses at several places, and this first one, negative 1, 1, is here. It has a mass of 3. 2, negative 1, we have a mass of 4. And at 3, 2, we have a mass of 8. So we have our masses here. And I want you to picture and our origin is right here. I want you to picture these are like a waiter or waitress at a bar, and they have a big beer on they they have a glass of wine, and then they have a shot of something. And each of those have a totally different mass, but you would imagine the big beer you would want towards the middle more, and then the other ones could be a little bit further away, the shot being the furthest away because it's so light. It's kind of like that. So let's jump into this and start by finding the overall mass. Let's do that. The mass is going to be 3 plus 4 plus 8, which gives us the 15. And so let's start by finding our moment with respect to y. That is going to be the first mass, which is going to be 3 times the first x coordinate, that's -1. Remember, it's the opposite. If it's y here, we're looking for the x values. X is going to be 4 times the x coordinate of the next one, that's 2, plus 8 times the x coordinate of the third one, which is 3. And when we multiply and add all those up, we end up with 29. Next up, our moment with respect to the x-axis is going to be the masses times the y-coordinates. It's 1 plus 4 times -1 plus 8 times 2. Add those up, we get 15. So what are the x-coordinates? X bar, remember, is m sub y divided by m, which in this case is 29 over 15. That's almost 2, right? If that was 30 over 15, that'd be 2. So that's the x coordinate. And you can see, here's my center of mass. It's about 2 over. And then for the y coordinate, I take 15 over 15, which is 1. So my center of mass is at the coordinate 29 over 15 and 1. So it's about 2 and 1. You can see for that system, that's about where that goes. So now we're going to up it even further. And we're going to talk about what if we want to find the center of mass of a plate. Now we're assuming that this plate is what's called the uniform density, meaning it's the same material everywhere on this plate. And we shouldn't care what the shape is. I mean, we will in the sense of we need a function that's going to work for us so we can do this mathematically. But we're looking for that point that if I were to balance this plate, I would put my finger underneath it and it would not fall over. It would be right in the exact spot here. I'm going to skip the physics behind where this comes from, but the A here represents the overall area of the entire system. And of course, we can always find the area of any function. That's the area under the curve, right? That's an integral. So we'll deal with that. And to find x bar, we're going to integrate from a to b, x times the function of x. And for the y coordinate, it's going to be 1/2 f of x squared. It's not real complicated where those come from. It's we're dealing again with the uniform density and all that kind of stuff. Okay, so let's do this. Find the center of mass of a semicircular plate of radius r. So let's start with our picture here. Here's a semicircular, meaning half a circle. There's our function, our f of x. And we don't know this yet. We're going to try to piece that together. And let's start out by finding the overall area. You can see that's part of both formulas. So we're looking at that. And that is going to be, because it's a circle, I could do an integral, but I'm not going to. Because it's a half a circle, pi r squared is a full circle. So this is going to be 1/2 of pi r squared. So each of these I'm going to be dividing by. So let's try to come up with our x bar is going to be 1 over pi r squared over 2. I'll fix that in just a moment. Times the integral from -r to r of x times the square root of r squared minus x squared dx. So that's our x times our f of x, which is here. Now, we're going to make things nice and simple here. This function right here is an odd function. How do I know that? If I take x and replace all of them with negative x's, that stays the same because I'm squaring it, but that becomes a negative x, meaning it becomes the negative of the function itself. That makes it odd. And when we integrate from negative r to r of an odd function, the result is always 0. So that was easy, not too bad. Let's take the other one, the y coordinate, y bar. And that's going to be 1 over a. I'm going to fix that up. I'm just going to make that 2 over pi r squared. The integral from negative r to r. Now this one, we have an extra 1/2 in here as part of the formula. And then f of x squared. So my f of x is here. When I square that, the radical goes away. And I'm going to note very nicely, that 2 and that 2, they go away. Clean that up a little. All right, just like we found out this one was odd, this one is even. I know that because when I replace x with negative x and then square it, I get the exact same function back. What that means is that I can do this. I can integrate and double it and just go from 0 to r. It's a very nice feature. All right, so we are going to end up with, let's push that up a little, 2 over pi r squared times r squared x. Remember, r is a constant relative to x, minus 1/3 x cubed from 0 to r. Now, when I plug in 0, they go away, so I'm only interested in the r's. When I plug in r, that's going to be r times r squared, that's r cubed. Minus when I plug in r there, that's going to be 1/3 r cubed. And I can see, if I get a common denominator here, a little bit more, you get 2 over pi r squared times 2/3, 2/3 r cubed. That's just doing 1 minus 1/3 is 2/3. And cleaning that up a bit, I'm going to get 4. Now notice all but one of the r's reduce out. 4r over 3 pi. So what is our center of mass? Is the coordinates 0, 4 over 3 pi r. There you have it. Now that's where they got that from. All right, we have one more to go. This one's going to be a little more involved, not much, just a little. And we're going to find the center of mass that is bounded by y equals cosine x, y equals 0, x equals 0, and x equals pi over 2. So let's draw that out just so we have an idea of what shape it is that we're even doing. And that is going to be, cosine starts up here at 1, and it crosses at pi over 2. So here is our plate. So let's start out by finding the area, since we need that for the formula. Oh, and I should point out this curve here. Y equals cosine of x. So that overall area is going to be the integral from 0 to pi over 2 cosine x dx. And it gives us sine x from 0 to pi over 2, which equals 1. That makes it very nice for us. We don't have to worry about dividing the 1 over a that is in the formula. So let's jump to it. Our x coordinate is going to be the integral. I'm skipping the 1 over a part, 0 to pi over 2, of x cosine x dx. All right, so this is going to involve by parts. So I'm going to go off to the side here and let u equal x dv is cosine x dx. du is dx, and v is sine x. So let's break that up. U times v is going to give me x sine x, that's going from 0 to pi over 2, minus the integral of v du, that's sine x dx, 0 to pi over 2. All right, when I plug in 0 there, that's clearly 0. When I plug in pi over 2, sine of pi over 2 is 1, so we just end up with pi over 2. That becomes plus, because the integral of sine is negative cosine. Cosine of x from 0 to pi over 2. Cosine at pi over 2, 2 plus cosine of pi over 2 is negative 1. Cosine of 0 is, I'm sorry, cosine of pi over 2 is 0 minus cosine of pi over 2 minus cosine of 0, which is 1, pardon me. There we go. So we end up with pi over 2 minus 1. That's my x coordinate. I'm going to leave it in that form for now. I don't want to break out the decimals. We could, but I'm not going to. So that's my x coordinate. Let's do our y coordinate now. Again, it's going to be 1 over a, and a we already know is 1, so we're going to skip that. And this is going to be 1/2 the integral from 0 to pi over 2 cosine squared of x dx. Well, if you remember, we have that. So I'm going to replace that there. Now I'm going to notice that I have the 1/2 times the 1/2. I'm just going to make that a 1/4. So 1/4 x from 0 to pi over 2 plus 1/2 sine of 2x from 0 to pi over 2. Now, very nicely, that goes to 0. When I plug in there, I get sine of pi, that's 0. When I plug in 0, I also get 0. This is gone, which leaves me with 1/4 times pi over 2. And when I plug in 0, it goes to 0, of course, which gives me overall pi over 8. So this means that the center of mass is at the coordinates pi over 2 minus 1, comma, pi over 8. And again, you could get a decimal breakdown of that if you wanted to. I hope that was helpful.